Hi guys, welcome to the introduction to geochemistry. In today's tutorial we will be talking about electron microscopy, and thus the electron and the interaction with the material that produce the energy in terms of photon. There is the which we're going to use in the energy dispersive X-ray technique. So here is the outline of the tutorial. It's pretty brief. We start with the electron and then the effect with the material, how they interact, and some working principle of the scanning electron microscopy, and what are some of the common operation in the electron microscopy. And then we'll go a little bit deeper in the X-ray spectroscopy. We'll also discuss some of the case study, some exercise, and some glimpse overview of the advanced electron microscopy. So now let's go to the first one, and how's the electron and materials interaction. Okay, now here is kind of a messy diagram of the interaction between electron and materials. What we have here in the left is the diagram of where we have the electron beam impinging on some kind of materials. As due to that impingement with bombardment from the electron beam, we have electron forming a kind of bell-shaped dumbbell inside what we normally call this as interaction volume. And because of this interaction, there's several effects that observe. One of them is the production of another electron, what we call the secondary electron. And one of those electrons, the original electron that we bombard to the sample, which we call a primary electron, bounce back, which that normally called as a backscatter electron. Another thing that we will use extensively in this tutorial as well as in the geochemistry is the interaction between the electron and the material that produce a photon with a certain wavelength that unique to a certain element, what they call the characteristic X-ray EDX. There's other kind of effect that's because caused by this interaction, but I will not be discussing much today. And the image on the right, the kind of much simpler schematic to show how those effects such as the secondary electron, the backscattered electron, and then the characteristic X-ray was generated. Okay, on the first one, let's focus on this one, the generation of secondary electron. So what happened here is that the primary electron, which is the electron we use to bombard a sample, interact with the atoms in the sample, whereby due to its high energy it could knock out some of the electron from the orbital of the atom. So this primary electron, because it's high energy, it may at some point eject more than one electron. So the ejected electron, or the donor electron, we call it secondary electron. And the second one is that in certain case, the primary electron, apart from knocking out a certain electron from the atom, it could also interact with the core of the sample, the core of the atom. So at some point, the primary electron is ejected back, which still have a high energy. That's what we call backscattered electron. Now the third one is at some point the primary electron eject another electron from a slightly inner shell of the atom. So the ejected electron, as we know previously, become a secondary electron. And in the wake of the missing of the electron, another electron from higher orbital may trying to fill the gap. Since the higher orbital has a higher energy, it has to release those energy to be able to occupy the inner orbital. So the energy that being released is in terms of photon. And It depends on what the element is. The wavelength of photon is distinct and some kind of unique to certain material, a certain element. So in geochemistry, we use this characteristic of X-ray, which is the X-ray that unique to certain element, to identify what kind of element that presents in the mineral or in the phase. Okay, now let's take a look what this electron microscope is. To be exact, it will be the scanning electron microscope. How the creature looks like, and then how does it work, and what we can use for it. So you have in this course, possibly you have access to two electron microscopy. One of them is in ASE, which is on the left here. This is the Joule 7800 field emission SEM, and the other one that you're probably going to have access to is the Joule electron probe microanalysis, Joule JX1. This is located at the FACS lab. I will be focusing more on the SEM in this discussion. So, and then the EPMA will be discussed in the different tutorial. So in this slide, I have the bare minimum schematic of the construction of the scanning electron microscope. So it's basically consists of the electron gun, where this is where we get the electron. Then electron was then pulled out by applying the gun voltage, and then accelerated down in the microscope column. Along the way it's down, it been conditioned by several sets of condenser lens, which is basically a magnetic field coil that introduces a magnetic field to bend the trajectory of the electron. So when it goes down, the electron may not have the same energy, and then this magnetic lens spread them apart, again converge them back and spread them back to get to filter away the unwanted electron with certain unwanted energy. So, and then after that it is being conditioned again. So once we have the electron energy, that spread of the electron energy that tight enough, and then in the final stage of the column we have a scanning coil that moves the electron back and forth, or scan the coil, the electron beam into the specimen that we're going to observe. So now earlier we have mentioned that due to the interaction of the electron beam with the material, there's several effects that being produced. One of those is the secondary electron. So a secondary electron that came out from the sample, my marker. So the secondary electron that came out from the sample being pulled to this detector and being used to make the image. So these are our secondary electron detector. And then apart from producing secondary electron, we also produce some X-ray, some of the X-ray characteristic. And we have here is the X-ray detector. This will collect the X-ray and then analyze them afterward in the computer somewhere here. And another one, a high energy electron that bounce back, that give you some other information, which is the backscatter electron, was captured by this detector here. So that's all like a basic principle how the scanning electron microscope works. Now back to this image, as corresponding to the schematic earlier, the electron source was up here and then being pulled down and accelerated by the electric field, goes down and being bent, spread and converged by the magnetic lens somewhere in the column here, and we have the aperture down here to filter out some of the unwanted electron. Now we have more than several detector here. One of these mentioned earlier is this is the X-ray detector that detect the X-ray emission. We have two of them, one in the back, one on the side, and we have the backscattered electron here. The detector is actually inside, which is the rod to move the electron in and out, and we can't see any of the secondary electron. It is inside the volume. So the sample that we analyze is loaded inside this chamber. So the chamber is kept in vacuum all the time. And for the EPMA, the electron source and the rest is basically the same, but instead of the EDS, EDS detector, which is electron energy dispersed spectroscopy, we have a WDS detector. So in EPMA we have 5 WDS detector and one of the EDS detector. WDS stands for wavelength dispersed spectroscopy. Now let's go through some of the operational of the SEM. So the two figures here is taken from the same spot on the sample. The image on the left here is the image formed by the electron that being detected on the backscattered electron detector, in short BSE detector. While on the right is the image that formed by the electron that being captured by the secondary electron detector. So on the right we can see that the image is much more contrast. So the contrast here is some kind of proportional to the atomic weight of the element that constitute of this mineral. So I guess this is a pyroxene mineral, silicate that contain iron, magnesium, and calcium. So the lighter element will appear darker, right? And while the heavier element will appear brighter. Okay, we can see that so this crystal was being encapsulated in the epoxy. So epoxy is much lower density than the mineral, so this way it's appear much darker. But the pyroxene contains a lot of iron, magnesium, silicon. They appear much brighter. Okay, on the right is the secondary electron image, which is the image that formed by the electron captured by the secondary electron. So we can have more detail here, but less contrast on the atomic weight. So we can still see some of the brightest, the heavier part of the sample to be a bit brighter, but it's not that contrasty. On the other hand, from this we can see more surface morphology. So for example, the epoxy that encapsulates this crystal shows the roughness. So this roughness came from the as a result of the burn mark by the huge explosion of the electron beam from the EPMA. So, and some other crack and some other small feature can highly visible from secondary electron image. So those two has a different function. So secondary electron is great to look for the morphological feature, like the roughness, how they change, how the shape. But the backscatter is great for making contrast between heavy element and then the lighter element. Now the other aspect of SEM operation is focusing. So focusing basically is to getting the electron beam size as small as possible. So here is the comparison between different size of the beam. The one on the left, relatively bigger beam compared to the right, and as a result we can see more detail, more like focus detail on the image on the right. So is one of the feature of the SEM is to get the beam as small as possible. Now Another aspect of the SEM operation probably that less being emphasized is apart from the size of the electron beam that impinges your sample, the other component is the shape of the electron beam. So ideally we would want to have a circular beam, but in some cases we may not have that. So, and we don't have a way directly to see what's the shape of the beam, but we can see the effect of the non-circular shape of the beam. So for this case, the beam circular form like a oval in the northwest and southeast direction, and the image resultant is kind of elongated in that direction. Similarly, the beam elongated to the northeast and southwest direction, that we can have the image elongation in the same direction as well. Now the last main aspect of the electron materials interaction that I want to emphasize here is the effect of the accelerating voltage, means how high is the energy of the electron that bombard your specimen. So if you look at in the column wise, where the top one is like a qualitative comparison between low accelerating voltage and higher accelerating voltage. The higher accelerating voltage causes the electron penetrate much deeper and then create a much larger interaction volume. So that may affect your larger interaction volume, may affect the resolution, the spatial resolution of your analysis. If you look at the row wise, is that there's also effect of the accelerating voltage and then the interaction volume due to the density of the your sample. The lower density will have the electron penetrate much deeper compared to the heavier element. So means that it's harder to the interaction volume will be much lesser or shallower in the heavier element. Now let's move on to the X-ray spectroscopy. So a little bit refresher about the X-ray characteristic X-ray that we discussed earlier is basically a extra energy that released by the transition of electron from higher energy state to lower energy state, that the energy releases in the form of photon, and those energy is kind of unique. Energy transition is unique to certain kind of material. So coming back to this image again for the third time. So refresher again, the X-ray detector that we have here. We have two of type. One of the energy dispersed X-ray, so it detects the energy of the X-ray. We have two in the Geochem, and on the other hand we have the WDS detector. So that's we use in the EPMA. So it detects the intensity of a certain wavelength. So why we have two different detector? Each of this detector has their strength and their weakness, and then depends on what the application is. One detector may be more suitable than the other. So on the bottom part here is some of the summary what the performance of each of the detector in terms of the sensitivity, the speed, the spectrum range, and the spectral resolution. So WDS tends to be less sensitive, but it's more common use for quantitative analysis, while the EDS is very sensitive. EDS is also very fast, and then one thing that makes it fast is because it's capture the entire spectrum simultaneously, whereby the WDS is only capturing one wavelength at a time. So that's the reason we have 5. So we can have 5 wavelengths to be detected simultaneously. So to make it clearer what I mean by the entire spectrum. So this here I have the simulated X-ray energy spectrum that due to interaction between electron and dioxide clinopyroxene. So due to the clinopyroxene consists of multiple elements. We have calcium, we have silicon, we have magnesium, we have oxygen. You will have a characteristic X-ray peak at different position. What is the EDS or EDX detector? So I would use EDX and EDS interchangeably because it's basically a synonym to each other. So in EDS, this entire spectrum is being captured simultaneously. So every recording, they record the entire spectrum. So in the one single acquisition, it captured the entire spectrum. That's why it makes it so fast. On the other hand, in the WDS, on this certain window of the spectrum is detected. For example, you have one spectrometer optimized for calcium, and the other one optimized for silicon, and the other one optimized for magnesium. So how that works, because the WDS use crystal that diffract certain wavelength that meet the criteria of the diffraction. What's the benefit with this? Why do people use this? We'll go that over to the next couple of slides. And so here is the comparison of the performance between the EDS and WDS. We have the EDS here. So in a single acquisition, we capture the energy of the X-ray from very low to very high. So what we're trying to look here, how can we, what's the performance when we use the comparator detector to detect the molybdenum sulfate. So the characteristic energy from these two elements is pretty close. So in WDS, sometimes the energy resolution was not that high. There's supposed to be two peaks here. But since we don't have enough resolution, it just appears as a single peak. On the other hand, in the WDS, we have quite stringent distinction angle because of the crystal diffraction, that WD has much more wavelength resolution, that these two closely separated spectrum can be resolved. But the time to take this spectrum is way much longer than time to take this spectrum, because in WD you have to scan what they call wave scan. They at a different diffraction angle to get this spectrum. Now here is the same result. So to make it more clearer, I put the energy of spectrum from EDS kind of zoom in to it. So basically no telltale sign where we can resolve the energy spectrum. Probably somewhere here that they overlap. So again, depends on what we're trying to do. One of the technique is much better compared to the other at certain case. Now let's go a little bit what the EDS is good for. One of them is the quick survey of the sample. What they call here is the qualitative X-ray analysis. In this example, we have a thin section that contains different mineral. We have a magnetite, we have olivine, we have pyroxene, we have plagioclase. How do we know this is what mineral? So we don't see the color, we don't see the extinction angle like in the optical. What we have in SEM, I maybe forgot to tell this, but SEM image is mostly black and white. So you have only black and white and brightness to tell you what the mineral is. So this is where the qualitative X-ray from EDS excel. So one of the example I put here is that how do you differentiate between an albite and anorthite? So this is a simulated pattern from Monte Carlo simulation. So we know that albite consists of sodium, aluminum, silicon, and oxygen. So from the EDS, we should look for the appearance of silicon, because mostly of silicon. We have look for the aluminum as sodium and oxygen. So there's nothing else. And how about anorthite? The difference is that in anorthite we don't have the sodium, so we would not expect to see a sodium peak. So here, and we'll be expecting to have a calcium. So you have a calcium. So this one of the telltale sign where we can use the qualitative X-ray to identify some other phase. Another example would be how to identify the olefin phase. So unlike the plagioclase, so the plagioclase doesn't have the magnesium, so that's one of the telltale sign. And also there's more heavier cation. Let's say you have 2 iron, 2 magnesium in the phosphorite, and then olefin basically a mixture of magnesium and iron, and 1 of the silicon. So in all of this case, the metallic component, or the 2 metal cation will be more than the silicon. We will expect the peak from those 2 will be higher. For example, this is iron. We don't have the magnesium in a firelight. The iron peak is higher than silicon, and also here in the phosphorite, the magnesium is higher than the silicon. And similar here, the general olefin will be the magnesium, and the iron will be higher than the silicon. One last case, probably the identification of the pyroxene member, whether it's augite, pigeonite, orthopyroxene, or cyanopyroxene. So in this case, the general formula of the pyroxene, we have the 2 metallic cation that occupy the M site, and the 2 silicon that occupy the tetrahedral site. So in this case, the number of cation almost the same, and then since the M site is split between the 2 cation, we'll see most of the time the silicon peak is higher than the metallic cation site. So this is the case of the dioxide. We have magnesium and calcium, and the similar thing by Heidelbergite. We have calcium and iron. Both of them has slightly lower peak intensity than the silicon. And ansatite as well. So the ansatite, this may be probably causing a confusion with the olefin, because the magnesium is slightly higher than the silicon. So, and the next aspect for the X-ray spectroscopy is the quantitative analysis. What I mean the quantitative here is that how do we change from the X-ray counts that we have from the measurement into element concentration. I will not discuss this much, but the main principle here is to use a standard material for each element that is being analyzed. So what we do is that to get a spectrum from the standard and the specimen at the same condition. What I mean the same condition would be the same focus point, the same accelerating voltage, the same working distance, and the same vacuum level, as much as possible the same. And the main principle to use to convert from the X-ray to quantitative concentration is to compare what's the difference between the intensity from the standard with those that unknown sample, and which correlate directly with the concentration of the unknown compared to the standard. Now, a little complication happen when the sample is not the same density as the standard. So what it does is that the unknown sample may have a different interaction volume as those that are standard. So it could be bigger, it could be smaller. And in that case, there's an iterative process that being done to adjust for that. They call matrix correction. The one that famously used is they call ZAF correction. The ZAF, the Z is representing atomic number correction, and the A is the absorption correction, and the F is the fluorescent, X-ray fluorescent effect. So the last part of on the quantitative X-ray spectroscopy operation is that the effect of the coding. So I hope I'm not too complex on this, but in order to do the X-ray spectroscopy in the SEM, you need the sample to be conductive, and most of the mineral sample, they are not conductive. So what we do normally is to coat the sample with conductive layers, and sometimes we use gold. Sometimes we use gold, and most of the time here we use a carbon coating. So I like to emphasize that adding the coating on the sample reduce the numbers of reduce the number of X-ray that being detected. So here's the comparison on the left without the coating. We kind of like have a normalized 546 detection, and the one on the right with this 10 nanometer of coating, we have like 480 relative detection. And on this case, I see try to get a little sense of how much each of the element is affected by coating. So generally all of them will have reduced X-ray intensity with the coating. So, and especially element that affected much is the silicon and oxygen. So we can see the trend reverse with the presence of coating and without the presence of coating. So the discussion will not be complete if we just talk about what's the strength of the technique that we use here. There are of course some limit to the X-ray spectroscopy. One is that it's polymorphism, so we won't be able to differentiate between two structures that have the same chemical composition. As we see earlier, we can't differentiate between firelite and phosphorite and statite. And this case, another example is we can't differentiate between graphene or carbon or diamond. So diamond and graphene diamonds make a 3D structure, a 3D carbon structure, where the graphene is make a sheet of carbon bond. So these two, because it's both of them made of carbon, so it will look the same in the EDX. And here in summary, I put the list of the limit to the X-ray spectroscopy. Of course, I discussed earlier, we have the polymorph problem where graphene versus diamond, quartz versus glass looks the same. And we have the trace element effect, like for example, ruby. Ruby is sapphire with the trace element of chromium and sapphire and blue sapphire. So these all will look the same. So basically, it's because that the detection limit for the X-ray spectroscopy is not that low. So it's basically helpless to detect any trace element. Another weakness, as I discussed earlier, is that the presence of peak overlap, that would not be possible. So molybdenum halide, tantalum halide, silicon, or oxygen with the chromium. Alright, here I have some of the cool thing that we have from X-ray analysis of the sample. Not instead of a single point spectrum collection. Here we can do some mapping as well. Means that we collect a certain intensity of the X-ray across entire area. So in the left here we have the backscatter image that collected by Jason, where the heavier mineral that contain heavier element or the higher density mineral appear to be brighter than those that with lower density. And the rest, the one on the right, is the map of the intensity on specifically correspond to iron. The one on the bottom is from the calcium mapping. Means that we collect only part of the spectrum that correspond to the calcium intensity. Okay, so earlier we have seen what's the analysis that we can done in the X-ray spectroscopy and the secondary electron scanning electron microscope. So what are the things we can do? So here I put some of the example that utilizing those techniques to find out what are the storage conditions that lead to explosive eruption of the Merapi in 2010. So this was paper by Fidel. They published in 2013. So one of the things that the analysis that came out with was the comparison between the 2006 texture and chemical composition with the 2010 eruption. So we know that 2006 was not as explosive as 2010. So where Fidel found that there's a more fresh amphibole was found in 2010. So, and while those in 2006, most of the amphibole has been degraded. So knowing the chemical composition and then how it changed across the different texture, and here there's also example and how can we deduce the time scale of this magnetic process. So in 2010, so we can see that the constant, for example, calcium may have a rich calcium on the outside and then lower concentration of calcium in the inside. And by utilizing the diffusion chronometry, we can be deduced what's time scale that this texture chemical zoning was recording. So getting the chemical composition will give you information how it changed and how fast the time scale of the magnetic process. So in this case, that the changes represent about between less than 2 years, 1.9 years, to maximum of 5 years of magnetic process that associated with the explosive eruption. So in the column wise here is the eruption from 2006. The time scale is between 2.4 or maximum 5 years. So it's pretty long time scale. Well, and the plot on the right here, the time scale that recorded by the chemical composition gradient is giving a time scale of less than 2 years most of the time. So it's kind of like a correlate kind of pattern that the fast movement lead to explosive eruption. This tutorial. So This is supposed to be a break when I do this in class, so but in this case I will be skipping this, and then I will leave all the exercise and Q&A for the in-person discussion. So I just go straight to the summary what we have discussed today. There are strength and limit to the SEM, to the geochemistry application. Good for morphology of solid and major chemical composition of the rock. So by using that and by knowing the morphology and composition, it might tell a story about the magmatic process and what's the happened before related to geological process from the geochemistry. So by that, I will end my tutorial for today, and I'll upload the entire stack of the slide with more information and some of the exercise in the Blackboard, so you can have a look at it and enjoy the rest of the course. Bye bye.